Welcome everybody to another technologycatalog.com webinar. My name is Vincent van Beuzenkom. I'm the CTO and co-founder of technologycatalog.com. Today we're joined by Harry Polman, who's the managing director of H2O Biofouling Solutions, and Harry will be presenting their Ecodosing technology. And it's very impressive, I can say, how we've seen while working with H2O Biofouling Solutions during the last couple of years, how they've managed to really combine the environmental aspects of biofouling control with also the great benefits that you as an operator can get in terms of OPEX reductions, integrity improvements, if you do your biofouling control in the right way. So very much looking forward to your presentation, Harry. Just one practical note for the attendees. If you have any questions for Harry during the presentation, you can just leave them in the chat function. I will then pick them up at the end of the presentation in the Q&A session. So Harry, I would like to hand over to you. I'll switch off my camera so you have the full screen for your slides, and then I'll get back to you during the Q&A.
Thank you, Vincent. Well, welcome everybody. My name is Harry Polman, Managing Director of the company H2O Biofouling Solutions. And today, the webinar, I like to present and give some insights in the technology Ecodosing we developed and how it can result in economical and environmental benefits for industrial water systems. Industries, they use large volumes of surface water, either for cooling purposes, for cooling their industrial processes like a power plant or an oil and gas installation, or as a source to produce potable water, for example, with desalination plants. Globally, the industry uses large volumes of water, and as you can see, there's an article was co-author where an overview was giving on the amount of seawater which was used for cooling, desalination, or ballast water treatment. And you can see for cooling water, an estimate of the power plants globally use 470 to 800 billion cubes per year. So we're talking about very big volumes. Seawater intake systems, they have the objective, as mentioned, to cool systems, remove heat from the processes or equipment, heating medium for LNG regasification plants, or provide a source for desalination plants to produce potable water. The design of an intake depends very much on the location, the type of utility, and also the allowance in the discharge permit. Intakes often are open intakes, as you can see on the picture on the right. This is one of the biggest cooling water systems in the world. It's in Jubail, Saudi Arabia. This is typically an open intake, but also you have intakes which have like a submerged intake dome below sea level. After the intake, there are filtering systems to remove larger debris from the water, so to not affect the operations of the plant. The residence time of a cooling water system or an intake for a desalination plant is usually relatively short. It can be a couple of minutes, but also can be extended to maybe an hour for very large complex systems. Biofouling, besides seawater, biofouling organisms enter the system. And these are some interesting pictures I'd like to share to give you some insight on the impact of biofouling in a seawater intake system. The picture on the left, I like a lot. It's actually a seawater pump, completely covered by a large amount of marine fouling organisms. The attachment and the rate of fouling, the picture you see, that occurred from a clean pump to this situation within 1 year. So the amount of biofouling can actually attach and grow in a very fast way in a seawater system. Fouling needs cleaning. So once your system is fouled, you need to clean it. And often it needs physical cleaning, like you see in some pictures, by actually people who have to dig out the fouling organisms from the system. The impact of biofouling can be quite severe. Biofouling can result directly in an unplanned outage of the system. Usually that's caused by head loss in an intake pipe, which increases wall roughness, which results in head loss in the intake pump basin, or blockage of your condenser heat exchanger. Biofouling has a big risk on operational reliability of the utility. It also reduces the thermal efficiency of the plant. It can increase the differential pressure on RO membranes as you get fouling on membranes. Biofouling always results in the need for more chemicals to clean it and to control the amount of biofouling in your system. And in cooling towers, biofouling can also result in a health risk for humans caused by the Legionella bacteria, which can be growing and multiplied when a biofilm exists in a cooling tower. Biofouling always results in higher operation and maintenance cost, and the impact can be easily more than $1 million per day. This is a nice schematic overview I once created to give some insight what will happen when you get settlement of marine fouling organisms in an intake pipe. Well, first of all, you get a technical impact. So the cross section of the pipe will be narrowed. A reduction of water flow will happen. You will get head loss. In the heat exchanger condenser, you get a loss of heat transfer efficiency, and biofouling can also result in corrosion, flow accelerated corrosion or microbial induced corrosion. This has a big impact on the technical reliability of the utility itself and results in ecological, environmental impacts. Head loss, you need more biocides, so you need to add more chemicals, which means you're discharging higher amounts of chemicals, which has an impact on the discharge water and the receiving water. More energy consumption by pumps, unscheduled outages, cleaning activities. They also result in more environmental impact, for example, increased carbon dioxide emission. Leakages caused by corrosion have an impact on the receiving water. Economical impact of settlement of fouling, well, profit loss, increased OPEX, loss of availability of the plant, more maintenance cost. And in the end of the day, what you see with marine biofouling, you get more cost, less output of your utility. So for all these reasons, it's very important to prevent the actual settlement of marine fouling species in your intake system. Marine fouling species, they settle in your intake pipes. And I present two pictures. The one on the left is a clean picture. Once it's submerged in seawater, what will happen in time is within a minute, already organic particles like proteins will attach to the pipe surface. This creates a layer which is attractive for bacteria to settle, and bacterial settlement will happen within 1 day. After bacteria settled, you get, for example, macroalgae or protozoa settlement, and within 2 or 3 weeks, the surface of the pipe is suitable for larvae of macrofouling organisms like mussels, barnacles, and oysters. A seawater intake system is generally designed to provide optimal conditions for marine biofouling larvae to settle and attach and grow. The velocities in an intake system are generally between 0.2 and 2 meters per second. This is a range which is optimal for these larvae to attach to the pipe surface and to get food and oxygen from the water system. There's turbulence in the system due to different diameters, bends in the pipes, and turbulence will facilitate preferred conditions for some type of larvae, for example, mussels. With the continuous flow of seawater, you provide these organisms continuously with sufficient nutrients and oxygen, which will stimulate growth of the animals. Screening, which is installed in an intake, will generally keep out predators from the intake system, which will make the system itself more safe habitat for the macrofouling species itself. During the construction of an intake, there is a significant risk biofouling settlement will happen during the construction phase. So once the plant starts to commission, already the pipes are fouled and head loss is already present in the seawater system. So special attention during the construction of a seawater intake system is something which we highly recommend to prevent already head loss before the actual commissioning of the utility. When these organisms settle, they settle in two different ways. Some organisms, like mussels, they use biological ropes, we call them bisus ropes, to attach to the pipe surface. The picture on the left, you can see very clearly these ropes. These ropes are very strong. But also, once you kill the animal, so once you kill a mussel, these ropes will dissolve and the shell itself will detach from the surface and flush out of the system. Other type of organisms, so for example, barnacles, you see on the right picture, they cement themselves to the surface. So once the larvae attaches to the pipe surface, it creates a calciferous product, which more or less the shell will be glued to the pipe surface. Once these animals are glued, you cannot remove the shells from the surface anymore, only with physical force. If you kill these animals with a biocide or with an effective treatment, you will kill the organism which is inside the shell, but the shell itself will remain on the pipe surface. So that also means that with the wall roughness created by these shells and the head loss caused by the wall roughness will not be eliminated once you already have settlement of these organisms on your pipe surface. Marine fouling, so when do the larvae will enter the pipe, they will settle. But when do they actually arrive in the pipe? Well, macrofouling species in the surrounding sea, they have a typical breeding period. During this breeding period, the adults release larvae to the water. It's important to understand that individual mussels, oysters, barnacles, they release a lot of larvae to the water. One oyster can release millions to hundreds of millions of larvae to the seawater. When all these larvae are present in the water, they will enter your seawater intake. There is no filtering system except beach wells. Otherwise, there is no filtering system which is capable of preventing ingress of these larvae. So these larvae will enter your system. And as explained in the previous slides, the conditions in the pipes are ideal for settlement and growth. The number of larvae and the growth rate of the species depends very much on the type of species, the availability of nutrients, and water temperature. So in regions where the water temperature is very stable, around 25 degrees, 25 degrees, you more or less have an ideal environment for these species to grow. When this is combined with a lot of availability of nutrients, you will see that these organisms grow very fast. Now, the picture on the right bottom is a picture of a oyster, and this oyster has a size bigger than the hand of an adult male. The size of these oysters, they grew from larvae to this size within 2 years in that specific location. This oyster was found during an outage of the plant. The intake pipe was cleaned, but the intake pipe was only operating for 2 years. So that means that the animal arrived as a larvae, grew due to the optimal conditions in the pipe to this size within 2 years' time. The graphical picture you see, the graph is a graph from an article I wrote in 2011 to get insight in the impact of increased wall roughness, growth rates of fouling species to head loss in an intake basin. And from a case study we took, we saw that biofouling organisms form a layer of fouling on the pipe surface, and that can grow to multiple centimeters in years. How do you prevent biofouling? Well, instead of just dosing a biocide, we combine with Ecodosing system characteristics, operational concerns, monitoring and control, and make a treatment choice. The design of Ecodosing is based on the local specific conditions, so based on the local biofouling species, water quality, seasonal effects, but also restrictions related to discharge permit allowance. The technology Ecodosing is not a new technology. It's been implemented now for more than 20 years and also acknowledged as a best available technology. The working principle is based on the reaction behavior of the animals. When you add a biocide to water, animals close their shell and switch from aerobic to anaerobic metabolism. They protect themselves. When the dosing stops, they open slowly. So if you have a continuous dosing, you see on the top graph, they will stay closed for a long period, use a little bit of energy just to stay alive. To get an effect, you need multiple weeks, months to actually get an effect on these organisms. With Ecodosing, we add some chlorine to water, they close, then we stop the dosing of a biocide and they open up again. And if you tailor the time periods and concentration of biocide dosing, you're creating a behavior where you force the animals to open and close continuously. This kind of behavior uses a lot of energy, and in practice, these animals exhaust themselves. So instead of trying to kill the animal with a biocide, you use the biocide as a trigger to stimulate the organisms to become highly active, so they exhaust themselves. In practice, you need a lower concentration. So if you have the orange line, a continuous dosing to be effective, Ecodosing needs a lower concentration because you don't need to kill them, you only need to trigger them to become highly active. You also don't need a shock dosing because a high concentration doesn't impact the animals because they protect themselves by closing the shells. After 24 years, we saw a lot of benefits. We applied the technology in many different types of industries, and basically we see three major benefits. Operational benefits, guarantee production capacity, no risk for outage due to biofouling. Economical benefits, no loss of production capacity of the plant and availability of the plant. The OPEX cost reduction is on an average 30 to 60%. Return on investment of the tuning, more or less, the dosing to Ecodosing is on an average between 3 months and 1 year. Environmental benefits, lower energy consumption due to a clean system, reduced amount of biocides, and reduced discharge of biocides and its byproducts with at least 50%. A clean system means optimal pump capacity, means less carbon dioxide emission. I'd like to share a few case studies. One of them is a power plant in the Netherlands, seawater cooled. This was the first location where we installed the technology back in 1998. So this plant is now operating for 24 years with Ecodosing. We never changed the time interval or concentration to control biofouling. Before Ecodosing, they had a continuous dosing, and as you can see, with the continuous dosing, there was still fouling in the system. They had an outage every 2 years to clean the whole system by hand, which was very costly and cost also quite some money because the plant could not produce power. In 1998, we tailored the dosing and switched from continuous to Ecodosing. We reduced the amount of chlorine dosed with about 50%. And these are the pictures you see in an outage of the plant. Every 4 years, the plant has an outage, and usually we do an inspection and we see these kind of pictures. Even after 24 years, we still see very clean cooling water system and a very clean condenser. This also means that the animals are not capable of adapting their behavior to a certain time interval and concentration. An LNG plant in Qatar, over here also continuous dosing, still fouling in the system, and Qatargas was challenged to reduce the discharge limit from 0.2 to 0.05. We installed Ecodosing, we reduced the amount of chlorine dosed to the intake with 56%, and what we saw is that this plant, you see the picture on the right, an improved fouling control. No fouling in the system anymore, clean system in comparison with continuous dosing. So with less chlorine, cleaner system. For Qatargas, it was important because the Ecodosing proved to be in compliance with the very strict discharge limits in Qatar for free residual chlorine. A seawater RO plant in Saudi Arabia, they started the plant in 2012, first of all with seawater which was continuously chlorinated. They neutralized it with sodium bisulfate, but they saw a lot of bacterial fouling on the RO membranes. So they switched to a system where there was no chlorination in the seawater intake. The quality of the membranes improved. The cleaning frequency was postponed from every 30 days with continuous chlorination to about every 3 months. But then they saw that there was marine fouling in the intake pipes and also in the pre-filtration system. We installed an Ecodosing at the seawater intake, and the plant is now operating for more than 5 years with Ecodosing. And what they saw was a clean seawater intake. You can see a picture on the right of the drum screen. That is clean, pipes are clean, no head loss, but also the fouling on the RO membrane didn't increase. Actually, the cleaning frequency was more postponed in due time and is now about every 5 months. So also for a seawater RO plant, Ecodosing proved to have significant benefits. And at the moment, we installed the technology at 5 seawater RO plants in the Gulf region. To maintain quality and to maintain an efficient biofouling control, we use biomonitoring systems. We use 2 types of biomonitoring systems. On the left, a picture of a probe to measure online the risk for buildup of biofilms. And on the right, it's our biovision monitor, which is connected to the seawater system and which will give insight in the risk for marine fouling species settlement and growth. By using biomonitoring, you can have a real-time check and an online control of the efficiency of your biofouling control procedure. Some concluding remarks. Ecodosing is acknowledged as the best available technology and being in compliance with the IPPC BREF document. It's a European document which more or less describes all the BOT technologies for power plants. Ecodosing philosophy has now a proven track record for more than 25 years. It's implemented in many different seawater intake systems around the world, typically at industries like power plants, oil and gas installations, LNG plants, LNG regasification plants, and seawater RO desalination. Ecodosing reduces the use of biocides to a minimum while securing operational reliability and production capacity. It proved that with reducing the amount of biocide, you actually improve operational reliability and biofouling control and can guarantee production capacity. It's important to take a proper biofouling control procedure into account in the design stage of a new plant, in a design stage of a new seawater intake. In addition, as mentioned earlier, there is a risk for during the construction site of a seawater intake. So a risk assessment of a possible risk for biofouling accumulation during the construction period is strongly advised to prevent head loss during the commissioning of the plant itself. I'd like to thank you for your attention and open the floor for questions.
Thanks very much, Ari. Great presentation and I guess some excellent case studies to support the performance of your product. And in a way, it's interesting to see that I guess the technology is still being underutilized, and while the case is so strong. So indeed, let's open the floor for questions. So for those of you that missed the introduction, you can leave your questions just by typing them in the chat function. I will then pick them up, and for the benefit of those that will be watching the recording later, I will actually read out the question, and then Harry can answer. So the first question coming in is, can ecodosage be applied on every seawater intake? What constraints do you have on the usage of ecodosage? For example, you spoke about the regulatory limits on discharge of chloride.
Yes, the question was a little bit hampering, but if I understood correctly, your question is about, okay, can ecodosing be applied at all different kinds of utilities? Also, whether there's a restriction more or less on chlorine in the discharge.
Right, yes.
Okay, well, ecodosing, to control biofouling, 2 numbers are generally important to take into account. The first one is, what kind of level of biocide do you need to prevent biofouling up to the critical point in your cooling water system, generally the heat exchanger condenser. The second number which we take into account is, what is the discharge level at that specific location? Because to control biofouling, you need to be efficient up to the inlet of the condenser, but you have to be in compliance with the discharge limits. And what we try to do is to try to find a balance between the lowest amount of chlorine or a biocide in general in the cooling water system itself, but be in compliance with the discharge. And so far, we are capable of finding this balance. And the example I showed with Qatargas in Qatar, where they have a very, very low discharge restriction, we were able to optimize biofouling control and stay within this low discharge limit.
Okay, yeah, thanks. And actually, you mentioned this. That was actually something that triggered me. Was you focus very much on chlorine, of course, but would it also work with other chemicals?
Yes, I mean, chlorine is mentioned because chlorine at the moment is still the most used biocide in the world, especially in seawater systems. However, the technology is based on the reactional behavior of the species to a biocide or a fouling treatment procedure. And we also have case studies where we used different products. For example, peracetic acid, chlorine dioxide. We also used brine in freshwater systems. So we always look at, okay, what is the best option for a specific location? Also taking into account different products.
All right, great. Actually, we have quite a number of questions coming in, so hopefully we can answer them all. So let me go to the next question. One question that came in, and perhaps this is a bit wider. I see multiple questions more or less on the same topic. So one question is around the applicability of the system if you also have reference cases, for example, for offshore platforms for the C2C cooling water systems.
Yes. Well, for offshore platforms, the technology itself will also be applicable. And if you, for example, set a specific time interval concentration at a platform, and there are multiple platforms in the area which uses the same seawater, same species, so it's like a very comparable location, then it's a matter of copy pasting more or less this regime to the different platforms, but tuning it on each platform itself, because the optimal time interval and concentration is something you need to apply at the inlet of the critical component in the system. So what you actually dose at the inlet due to residence times or the design of your seawater system itself, that can maybe need a little bit of adaptation on exactly how you're going to dose it. But in principle, it could be applied at multiple locations offshore if they are comparable with seawater quality and biofouling species.
All right. And then the other extreme, another question is, can it also be applied for sweetwater systems?
We also use it at sweetwater systems, for example, in the Netherlands, in rivers. It can also be applied. And one of the benefits we see in freshwater systems, like in the Netherlands, we reduce not just in time from continuous to intermittent dosing, but also the dosing is tuned to the season. And in the Netherlands, we see that ecodosing is only applied 6 to 8 weeks a year to control biofouling in a freshwater cool system, and it's power plant, waste incinerator, and refinery actually, which we apply in that way. So the overall cost and impact of chlorination can be significantly reduced.
Okay, and then next question. By exhausting the biofouling, does that mean that the mussels are present within the system at periods and the exhausting causes them to fall off, or that the mussels were never able to cement or anchor on the pipework in the first place?
Well, I think biofouling control, it depends on the utility. In seawater systems, where you have a risk of cementation, more or less, of these animals, so they glue themselves to the surface, you want to prevent settlement of larvae. So the technology is applied during the period where larvae are present in the water, and the technology itself will prevent larvae once they attach to get food and oxygen. So they will released again from the pipe surface and go through the system. In some freshwater systems where all the animals are able to be dispatched from the surface, in some situations we allow a little bit of growth and then apply ecodosing to exhaust them, kill them, and they can flush through the system and keep it clean in that way.
And I think actually there are two questions that relate to that particular item. Does it also mean that there's a requirement for filtration of the mussels to protect critical downstream components?
No, because like I said, and what we do in freshwater systems is we allow them to grow to, and it depends on the location. What the client also accepts. But what we do in the Netherlands, in these locations, we let the mussels grow to a certain size, a couple of millimeters, which when they die, they can still flush through the condenser. So they will not block a condenser or a system. And in that way, you can keep your system clean.
Okay, yeah. So I think that answered some of the questions that were coming in. People are definitely curious indeed if it flushes, that if there's no need to filter them out. So thanks for answering that. Then another question, this is more related to the applicability. So is ecodosing also suitable for closed cooling systems, like biofilm in paper mills?
Well, I think yes. However, to prevent biofilms in closed cooling tower systems, more or less, you need much less biocide dosing and a much shorter period of the time. And the biofilm probe I showed in the slide, that's a biofilm probe which can measure the buildup of a biofilm. And using this kind of probe, you can tune more or less your biocide dosing to an absolute minimum. And that generally in these systems is required for between 15 minutes and 1 hour a day. That should be sufficient to prevent any buildup of biofouling, biofilms.
Okay. So I think we're running out of time, but there's still quite some questions. So let's try and still answer a couple more. Interesting one, actually, topic that you've not discussed. Could it, in theory, also be applied for an open surface? So if you look at a hull of a ship, for example.
Well, I think for a ship hull, it's difficult because how do you expose them to like pulses of a biocide? And so it's typically more for pipe systems, although we also see it effectively being used in open intake channels. That also works. For ship hulls itself, I think there are other technologies which are more suitable for that specific application.
Yeah, I can see that. Yeah. Then let's end with a couple of practical questions for those interested really to apply this. So first question is, what type of polymer coating will be good in combination with ecodosing or the ecodosing system? So I guess that would be the coating on the pipework, internal coatings.
Yeah, well, if there is a coating, coatings generally prevent settlement. Some of the coating, like file and release coatings, for example, when they are very smooth. The downside of coatings is that they wear out in due time. So in due time, you will see that the coating will be less efficient to prevent settlement and growth of marine biofouling species. Also, velocity has a large impact on the efficiency of a coating. So the coating itself and ecodosing is something we sometimes combine, where we use a coating in a specific part of the intake system, which is difficult more or less to protect using a biocide. And that can be like a core screen or something like that. An offshore intake where the bar screens more or less on the intake dome to protect those from biofouling. A coating could be of added value, I think, for using a biocide with ecodosing.
All right. And maybe end up with a last question. So if some of the audience, if they are dealing with an old fully fouled system and they would like to switch to Ecodosing, what steps do they have to go through? Would you need particular filtering in place initially? Can you perhaps just give some indication on that? Maybe it's a bit case dependent.
Well, it is very case dependent, obviously, but these are projects we have executed also in the past, and the first step will be a risk assessment. So get insight in the type and amount of fouling in the system. Also get insight in if there is like filtration, are there mussel filters in front of the heat exchanger which could remove debris. So to make an overall assessment of what is in the system and what could be the risk more or less when this is released to the utility. Once we know the Ecodosing regime, so we're going to develop the Ecodosing regime, the optimal time interval and concentration for this location and these species. This development is done always separate from the utility itself. So it's in a mobile lab container on the local conditions. Once we know this, we generally start applying the Ecodosing regime using additional monitoring systems with adult fouling species in monitors we install in the system. And slowly we're going to increase the efficiency. And based on the mortality we measure, we can measure the cleaning rate within the system itself. And in that way, we are able to clean more or less the fouled system in a more controlled way. And by cleaning it in a controlled way, well, you can reduce the risk for the utility itself. Another option and a strategy we used is that, okay, when there is a scheduled outage of a utility, we start using Ecodosing like 4 or 5 weeks before, very intensively, and try to kill more or less and remove and exhaust as much as possible before the actual outage of the utility. And and try to handle the risk in that way. But that's always, the risk assessment is always a close cooperation with the operators of the plant itself to see, okay, what would be the best way to clean the system as much as possible with Ecodosing.
Okay, thank you very much. I think there's one question actually which I would still like to pick up because we missed that. Maybe that's, I think it was in your presentation. Somebody's asking, do you have a particular ratio if it comes down to injection rates for related to cube per hour for the injection rate of chemicals? I think that may be useful also in reference to what continuous chlorine injection systems may require.
Well, in principle, scale does not matter. So Ecodosing works in small seawater intake, small systems, but also very big systems. So the picture I showed, systems up to like 500 cubes per second. So very big seawater cooling systems. The technology works the same because it's a matter of trying to get these pulses, these time intervals of chlorine or biocide through the system efficiently. The dosing itself, so the dispersion of chlorine or the biocide at the intake, that needs some specific attention, and that's where we also add value to design intake dispersion systems. The amount of biocide you need, so how much capacity do you need, more or less, that's also something we support and we can deliver. But in principle, size does not matter for this technology.
Thanks. Yeah, and I think some of these questions are maybe going into the specific case requirements. So actually, I would like to invite anyone that has more questions or questions about your specific applications. If you go to the Ecodosing page on technologycatalog.com, you can also message Harry directly, and I'm sure he'll be happy to discuss further with you on your particular case. I think in view of time, I think let's start to wrap it up. But before we do so, any closing remarks from you, Harry?
Well, I'd like to thank you, Vincent, for the opportunity for this presentation, and I hope it was interesting for the audience. I appreciated all the questions, which are very good, actually. And as you mentioned, if there are more questions or people want to get more information or have a specific question about their utility, please send us a message and we will respond at the earliest.
That's great. Yeah, and I would also like to, thank you. Great presentation. I learned something again, especially the beginning about biofouling. It's not something I deal with every day. So great combination of some insights and case studies. So thanks for that. Thanks for the audience. Indeed, I think very active Q&A. And from our side, we hope to see you again for our next webinars. We will be taking a bit of a break towards the end of the year. So we're be kickstarting with a new series of webinars starting in January, but just keep on looking at the platform and you'll see the announcements for the next webinars coming up there. So thanks everyone and have a good day. Bye-bye.